Hello class, so today we're going to be talking about displacement, velocity, and acceleration graphs. Starting off with displacement versus time graphs. A displacement versus time graph is a thing where we're graphing the displacement or the position of the object versus the time of the object. Looking at it, it tells a little story. We can see here, if I was looking at this story comes in four little pieces. For the first second, the person's not moving anywhere. You can see they are staying at the position of 20 meters. Then, between 1 and 3 seconds, they're moving forward. They're going from 20 meters to 60 meters. And from 3 to 4.5 seconds, we can see that they're standing still again. Their position at 60 meters is unchanged. And lastly, between 4.5 and 6 seconds, we see that they're moving backwards, traveling from the 60-meter position all the way back to the 20-meter position. And so that's a little story. The person was standing still, moving forward, standing still, going backwards. These graphs are a great way for us to identify what's happening in a quick visual format. We can also determine the velocity from a displacement time graph. Since velocity, its definition is the rate of change of displacement, we can determine the instantaneous velocity by finding the slope at any given point, because the slope is a measure of the rate of change of whatever graph you're using. So if I was to find the instantaneous velocity at 2 seconds, I would want to determine this by determining the slope at 2 seconds. Now if we take a look at the 2-second period, we can see that it is a nice smooth line that actually shares a slope with all of the points between 1 and 3 seconds. So we can determine the slope at 2 seconds by finding the slope of the whole section, right, using our slope function, rise over run, or y2 minus y1 is x2 minus x1. And if I were to do that, I would choose 2 points, perhaps this point at the 1 second and this point at 3 seconds. And I would find the difference between my y values, 60 minus 20, and the difference between my x values, 3 minus 1, to find a grand total slope of 20 meters per second. The velocity at 2 seconds is 20 meters per second, just like the velocity for this whole bit. Now, that's very nice when you have a nice direct line, but sometimes you can find the instantaneous velocity of curved slopes. If the line is curved, like we see this red function here, then you can approximate the slope by using something called a tangent line. A tangent line is a line that you create, that you draw to just touch the curve, but not to actually cross it at any point. It just touches the point where you're trying to determine the slope. That's the value, that is the line that we call the tangent line. We're not going to be doing those in class, but it's good to know just in case. So that's the instantaneous velocity. You can get it by either drawing a tangent line, or if there's a section that's uniform, then you go ahead and find the slope of that whole section. The average velocity, it's the slope from the start to the end of a whole time period. What you do there is you can set this time period for any sort of thing. So you place a point at the starting of the time period, and you place a point at the end of the time period. You draw a straight line, and you find a slope of that line. So if I use the example of determining the average velocity over the whole movement, I'm going to put a point at my starting, which is the start of the movement, and a point at my ending, which is the end of the movement. I draw a straight line between the two, and we determine the slope. The slope here is a horizontal line. It's a zero slope, or we can see the calculation over on the side there. But horizontal lines are zero slope situations. So we can see over the whole motion, the average velocity is 0. We can also utilize our displacement time graphs to get a visualization of the velocity is in a time-by-time section. In other words, we can use a displacement time graph to create a velocity time graph that matches the motion. If we're taking a look at this, we can see that there are 1, 2, 3, 4, there are 4 different motions that are actually happening here. do not try to make your velocity time graph in just one big go. There are 4 different motions. The best bet is to split it into 4 pieces. So you can see I've split my displacement time graph into the 4 separate motions, my 4 straight lines, and I can use the exact same time periods to split my velocity time graph. From there, you're just trying to find the slope of each section, and the value of the slope on the position time graph is going to be the value of the velocity time graph. The slope here is 1, so that means the velocity is 1. So on my velocity graph, I just put a line here at 1. For section B, we see that it's horizontal. The slope is 0, so I just highlight 0 on my velocity time graph. For section C, we see that it's actually heading down, and so it has a slope of -3. And so I have a value of -3 for my section C. And in section D, it has a slope of 2/5. 2/5 approximates to 0.4. So I did my best to approximate 0.4 on my graph. Now, velocity time graphs, they tell us a motion just like our displacement time graphs, but it's sometimes a little harder to read. When we see a graph, one of our first instincts is to think position time graph. With this one, it's a little bit harder, but if you take a moment, you can still read it. We can see this happening in 1, 2, 3, 4, 5, 6 different motions. Let's see if we can understand what's happening. For the first motion, I start at a velocity of 1 and go to 4. This object is speeding up, and it's in the positive direction, so it's getting faster going forwards. The next one, it goes from 4 meters per second to 0 meters per second, which is a stop. So it's going from 4 meters per second to a stop. It's slowing down, but since you notice the velocity is still in the positive direction, it's still moving forward. If I was in a car, I would imagine it as I'm rolling forward but stepping on the brake, so I come to a stop. So if I were to recap my first 2 bits, I'm speeding up while going forward, then I slow down to a stop, still moving forward. After that, we see that we now move into the negative velocity range. That means I now have a negative slope, or I'm moving backwards. So I begin moving backwards and my velocity is getting more and more negative, so I'm speeding up going backwards. Between 7 and 11 seconds, this flat line means my velocity remains unchanged. I'm moving backwards at a constant velocity, and then from 11 to 13 seconds, it goes up to 0. Remember, 0 is coming to a stop, so I'm actually slowing down to a stop, still moving backwards because the velocity is still negative. And then, after 13 seconds, it stays constant at 0. I have stopped. So if I was to imagine this situation as if I'm in a car, I sped up going forward, and then I slowed down to a stop. Then I reversed, speeding up, reversed at a constant speed for a while, and then came back to a stop, and then stayed at a stop. It's a little harder to read. Each time I needed to talk about what I'm doing to my velocity rather than just saying I'm going forwards, backwards, because it's not as directly, it doesn't just fit in our brains quite as nicely. So it takes a little bit more time, but hopefully you can see it's still manageable. Now, displacement can be found from a velocity time graph with 2 different ways. The first method we're going to talk about is that displacement is the product of an average velocity and the time interval that it occurs at. So displacement is average velocity multiplied by time. And if you have a uniform change, so a straight line change, you can find the average velocity by taking your starting velocity and your ending velocity, adding them together, divide by 2. So if I utilize this, the displacement between 2 and 4 seconds, well, I would take my starting velocity, 4, and my final velocity, 0, and divide by 2. That would give me an average of 2. And this occurs between 2 and 4 seconds. 2 and 4 seconds is a time interval of 2 seconds. So 2 times 2 is 4. 4 meters is how far it went in this slowing down portion. Another way that we can find the displacement is by finding the area between the line and the x-axis on the velocity time graph. So I sectioned off this section between 2 and 4 seconds, and we see that it creates a triangle. So I know that the area of a triangle is the base multiplied by the height divided by 2. And looking at this, 4 times 2 over 2 equals 4. There we go. So I just used my area of a triangle to get the area right there. And we notice it's the exact same answer, which it should be, because it's asking the exact same question. Now, acceleration has a key definition. It is defined as the rate of change of velocity. So very much how like velocity is the rate of change of displacement, we can find a very similar set of relations between acceleration and velocity that we find between velocity and displacement. Key here, since the slope of a displacement time graph is velocity, we can see that the slope of a velocity time graph will be the acceleration. And these relations are exactly the same. So continuing on with the concept of acceleration, we can see that this is a velocity time graph. We can see this object, its velocity is in the negatives, so that means it's moving backwards if we call it backwards negative. However, it has a positive slope, and so we would say that it has a positive acceleration. Now, one thing that we can note here is if my velocity is negative, but my acceleration is positive, that the velocity is getting closer and closer to 0 with each moment. That means when my acceleration and velocity vectors are in opposite directions, velocity negative, acceleration positive, the object is slowing down. Looking at the second graph that we see that's doing the same thing, this object is now moving forwards. The velocity is positive, but this is a negative slope, so positive velocity, negative acceleration means that it is slowing down, and you can see moment by moment it's getting closer to 0. If I wanted something to speed up, I would have to have my velocity and my acceleration be in the same direction. That way, say I started here with my positive velocity, if I grew with a positive slope, it would be increasing moment by moment, and so positive velocity, positive acceleration is a speeding up sort of situation. When we talk about slowing down, speeding up, these are kind of the scalar equivalents of acceleration. There is no true scalar equivalent of acceleration, but the slowing down, speeding up are kind of the real interpretations of our mathematical acceleration value. So we'll often be using acceleration, but it's good for us to talk about what's the real interpretation. Is something speeding up or something slowing down because of it? Hopefully that wasn't too fast, but hopefully that helps you out. I hope you guys have a good day and best of luck.